In part 2 of this video, we'll take a look at this schematic and see if we can make some sense out of this hodgepodge of stuff. RCA actually crammed quite a bit of features into this 2 vacuum tube 4 triode system. Let's look at the power supply first. This indicates an optional 3-wire power cord. If it is a 3-wire, the ground pin's connected to the chassis. We have a 120 volt primary with a neon bulb and a current limiting resistor to indicate power on off. We have a switch. Note that this 3-wire line cord is optional, and note that some of these have provisions for 120 volt primary connection to the transformer, which is here or here. So we have a single voltage transformer and we have the optional dual voltage transformer. Transformer has 2 secondaries on it. This one here, which is green and green-yellow, is a 6.3 volt winding, and it's used to power the filaments of the 2 vacuum tubes. Now, traditionally, the U.S. nomenclature for a small or miniature vacuum tube, the first 2 digits is the filament or heater voltage. In the case of a 1287, we would have to allow 12 volts to illuminate the filaments. If this were a 6J6, it would be a 6 volt filament. If it were a 117N7, it would be a 117 volt filament. If it were a 0A2, it would have no filament voltage. And that's correct. An OA2, more properly called a 0A2, has no filament. So the filament voltage is 0. Okay, why do we have a 6.3 volt winding for a 12 volt tube? This is very common. Here's the filament. One lead of the filament goes up to pin 5. The other lead of the filament goes to pin 4. If I apply 12 volts across here, this thing lights up. However, note that this filament is shown center tapped out to pin 9. If I apply a voltage between 5 and 9, half of this filament lights. Between 4 and 9, the other half lights. I have the option of powering the filaments or heaters in series at 12.6 volts or in parallel at 6.3 volts. This usually only happens with a 12 volt miniature vacuum tube. And bear in mind that 6.3 volts is the equivalent of 3 lead acid cells, each with a voltage of 2.1 volts, connected in series. Or 12.6 volts is a 6-cell series connected lead acid battery. This is what you would find in a normal car today. This dates back to the days when the heater or the filament voltage was powered by lead acid cells. So we actually see 2 filaments indicated here in parallel. So this 6.3 volt winding just powers the heaters or the filaments in the vacuum tube. Note that there's a wire leaving here. It taps 6.3 volts AC off for use somewhere else. We'll get to that. I'm not sure what voltage this winding is, but when it's rectified by a half-wave rectifier, there's a 40 microfarad filter capacitor here, and another 40 meg. That delivers 150 volts. We have a 6.3 volt supply here, which is just used for these filaments and something else. And we have 150 volts for use on the vacuum tubes. Let's look first at this switch and this knob. The switch is actually a 4-layer switch with a bunch of positions. How many did we say? I guess 8 positions. Selecting 6 coils that determine frequency range. Here it is, 85 to 200 kilocycles, 200 to 550, 550, so on. Now, the variable capacitor that's hooked to the frequency selection dial is this one up here. This, in conjunction with these 6 coils, one at a time, are the frequency output ranges. Note that there's taps on these coils. Well, these 6. That's because this is a Hartley oscillator. A Hartley oscillator has a tuned circuit, a coil, and a capacitor, sometimes called a tank circuit. And the coil is tapped. The output of the amplifier, whether it's a transistor amplifier or a vacuum tube amplifier, the output's taken here. So one side of the tank circuit or tuned circuit is connected through this capacitor to here. The tap on the coil, and this is not necessarily a center tap, is connected to common or to ground. The lower end of the tank circuit is connected to the input of the amplifier, whether it's a vacuum tube or a bipolar transistor. Okay, Hartley oscillator. If you remember the last video where I had the 191, we had a Colpitts oscillator. It consisted of a coil over here and 2 capacitors with the center connection of the capacitors to ground or common. So Colpitts capacitor, Hartley coil. The output from this oscillator stage is taken here and placed on the input or the grid of a second amplifier stage. Plate voltage is taken directly from the power supply up to here. There's no resistors, anything. And the output of this amplifier is taken across a resistor connected to the cathode. This is commonly called a cathode follower or an emitter follower. Cathode in the case of vacuum tube, emitter in the case of a NPN bipolar transistor. This is a fairly high impedance signal, and it's directly connected to our tank circuit. This amplifier has a gain of 0.9 or 0.8. So the voltage out here is less than here. There are two load resistors here in series. The output is taken across the full value of the load resistors, or 1/10 the value, depending on the high-low switch. It's then fed through a 100 ohm resistor to a potentiometer, through a DC blocking capacitor to the output. This is the BNC connector. I found a much clearer schematic on the web, and I posted all this information in the proverbial subdirectory below. So we've looked at this first oscillator. Let's take a look at this second oscillator. This is one of the 4 triodes, and it consists of a triode, some capacitor and resistor on the grid circuit to ground, a quartz crystal, which is not installed with the signal generator, it's an option, a quartz crystal. That quartz crystal will be connected between the grid and the plate, which in this case is at 30 volts. So plate voltage is coming down here, and applied to the plate. So this 30 volts appears on the crystal circuit in front of the signal generator. This comprises, comes down here, a Pierce oscillator. A Pierce oscillator is one where, for the most part, especially in our case, there's only one tuned circuit in the oscillator, and that's the crystal, quartz crystal. And it's connected between the voltage supplying power to the amplifier, which in this case comes through as RF choke. And the voltage here is isolated from the crystal by this capacitor. But in any event, the crystal, the resonant circuit that the crystal represents, is connected between high voltage side of the amplifier and the input to the amplifier. Output is normally taken from the high voltage side through a voltage blocking capacitor and out. Here's the same thing for a vacuum tube. Crystals connected between the plate, which is at some positive voltage, and between the grid. The difference is that on our circuit, the output is not taken from here. In our circuit, they've inserted a couple of resistors here. Two of them to be exact. And they've taken the output either here or here through a switch. Called high and low. So we have essentially the same sort of thing we had up here with a cathode follower with two resistors and a switch, high and low. Here the cathode comes down through two resistors, high and low, and the output goes up here. Remember, the output from the variable oscillator comes down here to this point. So we have both signals here and here applied across here, high-low switch, potentiometer, out. I just noticed this schematic shows a piece of coaxial cable with some clip leads. Where the other schematic shows a connector and a piece of coaxial cable and clip leads. This high-low switch varies the amplitude of the Pierce oscillator up here. This high-low switch and this potentiometer varies the combined outputs. Now we'll go to the third oscillator that's inside this signal generator, and this is an audio oscillator. Whenever this internal, external, and sweep switch is in the internal position. So when these two switches are in the down position, really it's one switch connected together. This forms a 400 cycle audio oscillator whose output is here, developed across this resistor, potentiometer, and presented to this output jack. So this is an audio oscillator inside the RF signal generator that, with the switch shown as it is here, presents audio to this jack here that can be varied in volume or in the voltage by this potentiometer. Now, this red line, which I painted on here, is nominally 130 volts. It comes from the 150 volt supply, but it passes through this secondary, this transformer, or this resistor, out the tap on the resistor, and up here. So, since there's AC 400 hertz voltage impressed across this resistor, that results in this voltage varying up and down 400 times a second. Well, this voltage is the source of power for both the Pierce oscillator here and the VFO. So this oscillator with a variable output here causes the VFO or the Pierce oscillator to be amplitude modulated. Remember, the output of these oscillators is proportional to the voltage supplied to them. And the voltage is caused to vary by this AC impressed upon this potentiometer from this oscillator. I can vary the amount of modulation with this pot called percent of modulation. This is also the pot that is output level for this jack. If we move into the external modulation position, that removes the grid circuit from this coil. It removes the plate voltage from this plate, this tube. So of course this oscillator stops. At this point, if I feed audio or some low frequency signal in there, that signal becomes impressed across the portion of the potentiometer that remains in the circuit. It's variable from 0 to what? Full. Well, I'm impressing an AC voltage from here onto here which ends up riding on top of the 130 volts to here. So I'm externally modulating, amplitude modulating, these oscillators. So there's a lot of stuff happening in this little package. One oscillator, two oscillator, a third oscillator some of the time. Internal or external modulation, and the ability to cause sweep to these two frequencies. We'll get to sweep in a separate video. In the next video, which will be part 3, we'll look at the output signal in various conditions. RF conditions, an oscillator, crystal oscillator, and we'll see modulation both internal and external. I'll save sweep for another video. So I hope this half-assed discussion explains some of the circuitry here. This amplifier sells for about $50 on eBay. It's a solid-state version. The C version sells for about $150. Thank you.